Okay, today, guys, we're going to be going over a brief lesson on rate equations. Okay, so we're going to focus on the differential rate law. Okay, so this is going to be 7-1, 7-2. It's not going to be all of it. I'm not going to talk about reaction mechanisms in this lesson, so I'll have another lesson discussing reaction mechanisms and how you can determine the rate equation from a reaction mechanism or vice versa. But today is just going to focus on the differential rate law, the rate equation for a chemical reaction, what it is, how do you find it, and if you're asked to show the rate law, what you need to represent, and then also some other types of questions you'll see that go hand in hand with the differential rate equation. Okay, so let's go ahead and focus on that stuff. All right, so looking at the notes, okay, so when we say rate laws, there's actually two types of rate laws. And the integrated rate laws, they are on your formula sheet. We'll have another lesson discussing the integrated rate laws down the road, okay? So this integrated rate law is really 7-3, 7-4. We're going to focus on the differential rate law. So the two types are, and if you are in calculus or you've taken calculus, then maybe you kind of understand the reference. We got the differential and we got the integrated rate law. So if I ask you for the rate equation for a reaction, I'm asking you for the differential rate law. So anytime you hear, hey, what's the rate law? We're assuming it's the differential rate law. So you should know the difference between the two. And again, we'll focus on the integrated rate law down later on this unit. But right now, the differential rate law, what it shows us is an equation that shows us how the rate of reaction changes with respect to the concentrations of the reactants. So it's really a rate law that shows how rate changes as we adjust the concentrations of our reactants. So, if I increase the concentration of my reactant, what happens to the rate? Does it get faster? Does it get slower? That kind of thing. All right, so the differential rate law shows us how the rate depends on our initial concentrations of reactants. And notice, it's reactants, nothing to do with the products, okay? The integrated rate law shows how concentrations of reactants change with time. So depending on what we know about the reactants, we can use the correct integrated rate law to maybe calculate how much of this reactant I'm going to have after the reaction is running for 20 seconds. So if I start with this much of reactant A, how much of reactant A will I have left, or how much of reactant A will be consumed in 20 seconds, 30 seconds, 5 hours, whatever. Okay, so this shows how concentrations change with time. And the differential rate law, the rate law we're going to focus on today, is how reaction rate changes with concentration, okay? So again, we're going to focus on the differential rate law. Sometimes it's just called the rate equation, okay? So every reaction can have a rate equation, okay? And it depends on the mechanism of the reaction, which we're going to talk about later. But every reaction has a rate equation, okay? So if I was asked, we've used this reaction a lot. If I give you a chemical reaction, I ask you for the rate law for this reaction, I'm looking for something that looks like this. So my two reactants here are hydrogen and nitrogen. And what I would represent is I would say the rate of reaction equals K. And notice this is kind of the lowercase k, all right? Times the concentration of one of my reactants, hydrogen, raised to the X, we're going to talk about what that is, times the concentration of nitrogen raised to the Y. Now, sometimes X and Y might be the same number, they might be different numbers, we'll talk about that. But this is what I would show. And really, the only thing, if all I was asked for the rate equation, I'd have to figure out what X and Y are. And X comes out to be 1 and Y comes out to be 2, I would plug in a 1 here and a 2 here, and that would be the rate law. That's what I would need to represent. All right, so let's talk about what those are. Okay, so notice that I didn't automatically come here and put a 3 for X, and I didn't put a 1 for Y. Maybe it's 3, maybe it's 1, probably not, but what we want to get away from is the rate law, writing the rate law. We aren't including any of the products. So notice, for like the equilibrium constant, we would do products over reactants, the coefficients become exponents. Okay. For rate equation, it's just reactants times reactants, and we raise them to not necessarily the coefficients. So you're not going to automatically say, oh, I'll put a 3 here and a 1 here. A lot of people make that mistake because we've done equilibrium expressions so much that we just get used to putting whatever coefficient is as our exponent, but that's not what we're going to do. All right, so a couple things to notice. All right, we only include reactants, so we're never going to have products in there. There's other things that we might include, but we'll come to that later when we talk about reaction mechanisms. Right now, the only thing for this I would have to include, unless I was given more information, would be the reactants. So you only include the reactants. K is the rate law constant. It's not the same thing as the equilibrium constant. It's lowercase k, it's not capital K. Equilibrium constant is capital K, the rate law constant, K, is lowercase k. So it's not the same thing, all right? But we would always have a rate law constant. So we say rate equals K, and then we do reactants raised to a certain exponent, and then times the other reactant raised to a certain exponent. If we had 3 reactants, we'd have 3 things here raised to a certain exponent, okay? If we had 5 reactants, we would have all 5 reactants listed here raised to a certain exponent, okay? Now, what are those exponents? So in this rate equation, the way I have it written, X and Y would be the reactant orders, okay? So in order to write a rate equation, a rate law for a reaction, what you need to do is determine the reactant orders. You need to determine the order with respect to reactant A, and the order with respect to reactant B, reactant C, and so on, and those will be your exponents there in the rate equation. All right, so in this scenario, X would be the order with respect to hydrogen, and Y would be the order with respect to nitrogen. So what I would need to do is find those reactant orders, and if I found them, then I just plug those numbers in where X and Y are, and that is the rate law. That's what I would have to write. Okay. All right, so again, X and Y could be the coefficients. Again, we'll talk about when they might be the coefficients when we get to the reaction mechanism. Okay, that's what we're going to focus on. Okay, but they're usually not the coefficients. Okay, they're usually not the coefficients. So don't make that mistake. Okay, so again, to figure out the rate equation for this reaction, we have to determine the reactant orders, X and Y in this case. Okay, so we have to figure that out. All right, so first off, what are the reactants orders? Now, technically you could have a reactant order that's 3rd order and maybe 4th order, theoretically. I've never seen it. It's nothing I've ever seen when I was studying chemistry in college. It's not a thing, and when we discuss this in class, it'll make more sense why it's probably not a possibility. So the reactant orders are going to be 0th order, 0 ordered, 1st ordered, 2nd ordered. Those are going to be your possibilities. So now, if we go back to here, this is either going to be a 0, a 1, or a 2, and this is going to be either a 0, a 1, or a 2. That's what the possibilities are going to be, okay? That's what I'm looking for. So the question is hydrogen 0 ordered? Is it 1st ordered, or is it 2nd ordered? And the same thing with nitrogen. Is nitrogen 0 ordered, 1st ordered, or 2nd ordered, okay? Now, what does it mean? Well, if we look at the equation, remember, think, now if you plugged in a 0 here, what would that mean? Remember, this is concentration of hydrogen, and what we're saying is the rate is going to change depending on these concentrations, okay? But if this is a 0, what would that mean? It would mean no matter what I plug in here, what's anything to the 0 power? It's 1. So if a reactant is 0 order, it doesn't matter what you do to the concentration, the rate's going to stay the same. So that's how you determine it. Okay. What happens if it's a 1? Well, whatever I do to the concentration, the same thing's going to happen to the rate. If I double the concentration, the rate's going to double. But what if it's a 2? What if the reactant order is a 2? What if I have a plug in a 2 here? Well, what if I double the concentration? The rate's going to end up being quadrupled. Okay, so that's the idea of reactant order. So let's talk about it. All right. So how do you know if you have a zero ordered reactant? Okay. Well, you know if you change the concentration of the reactant, but there's no effect on the rate. So I double it, but the rate stays the same. I cut it in half, the rate stays the same. I triple it, I quadruple it, I add 10 times the amount of reactant, but the rate stays the same. If changing the concentration does not affect the rate, then whatever the reactant is you're changing the concentration of is zero ordered. Okay? Well, how do you know if you have a first order reactant? Okay? Whatever change you do to the concentration, the same thing happens to the rate. So if I double the concentration, the rate also doubles. If I cut the concentration in half, the rate would cut in half, right? So if I quadrupled the concentration, the rate would also quadruple. All right, so if whatever change you make to the concentration of the reactant, if the same thing happens to the rate, you know you have a first order reactant, okay? And then a second order reactant is going to be whatever change you make to the concentration, the rate gets multiplied by that same change squared. So the way to think about it is if you double the concentration, the rate's quadrupled. If you triple the concentration, the rate gets multiplied by 9, right? 3 squared. If you cut the concentration in half, the rate will be multiplied by 1/4, right? 1/2 squared. All right, so that's how you know if you have a second ordered reactant. All right, and that's basically what your possibilities are. All right. So the way you figure out the reactant orders, you either have to be told, like maybe you're told, hey, we doubled the concentration and the rate also doubled. All right, now I know I have a first order reactant. Or we cut it in half, but the rate got divided by 4. So it's a second order reactant. Or we cut it in half and the rate stayed the same. Okay, so it's zero ordered. So you'd be told somehow, or you could use data, which I'm going to show you how to in a second how to do. All right, but let's go back to this equation. So let's say you find that hydrogen is first order and nitrogen is second order. All right. So here's the equation, and you're told hydrogen's first order and nitrogen's second order, and you want to write the rate law. Then this is how you would write it. You would say rate equals K, concentration of hydrogen raised to the first power. Okay, 1's understood, so you don't have to put it there, but if you want to put a 1 there, that's fine, times nitrogen squared. And that would be the rate equation. Okay. Well, what if hydrogen was first and nitrogen was 0? Then this is what you would write, but notice that anything to the 0 power is really 1, so this is really how it would probably come out. You would say rate equals K times the concentration of hydrogen raised to the first power, and you wouldn't throw in the nitrogen because it was 0 order. So like on free response, you could write it this way if you wanted to, or but the way you probably see it on multiple choice is that would be the correct answer. Okay. What if they were both first order? Okay, then this is what my rate equation would look like. What if they were both second order? Then this is what my rate equation would look like, right? Rate equals K times the concentration of hydrogen squared times the concentration of nitrogen squared. All right. And then if I didn't write it up here, but if nitrogen was first and hydrogen was 0, then it would just be rate equals K times the concentration of nitrogen, and that would be it. And you wouldn't include the hydrogen if it was 0 order. Okay. All right. So a couple things to know. Sometimes you're asked, after you determine, or it's been determined, each reactant orders. Like, so the reaction order with respect to each reactant, meaning like, so if this is my rate equation, the reaction order with respect to hydrogen is second, and with respect to nitrogen is also second. Sometimes you're asked for the overall reaction order, and that's really easy. It's just the sum of the reactant orders. So if this is my rate law, the reaction order is 3, right? 1 plus 2. If this is my rate law, then my reaction order would be 1 because I only have 1 here. If this were my rate law, then 1 plus 1, my reaction order would be 2. And if this is my rate law, then my reaction order would be 4, 2 plus 2. So with respect to nitrogen, it's second. With respect to hydrogen, it's second. Overall, it would be 4. Okay. Sometimes it's just a question that's asked, and all you have to do is add them up, and it's pretty easy. All right. All right. So here's kind of another thing to take from what we've been talking about. What if you were given the equation and you were told, here's the rate law? What does that tell you? So what you would say is, hey, okay, well, it tells me nitrogen's first order, but it's also, if hydrogen isn't included, right, and the rate law needs to include all the reactants, the only time a reactant wouldn't be included in the rate equation is if it was 0 order. So given this equation and given this rate law, I can conclude that hydrogen must be a 0 order reactant. So anytime you have a reactant that's in the overall reaction, but it's not included in the rate equation, the conclusion to come from that is that that reactant that's not included in the rate equation must be 0 ordered. Okay. All right. So how do you determine reactant order? There's really only 2 ways you can do it, and really there's only one way to do it, but in AP chemistry, like on the test, it would be 2 different ways, right? So you have to use experimental data. All right, I'm going to show you how to do that. Or you have to use a reaction mechanism. So we're not going to talk about mechanisms today. I'll say that for another lesson. But if you have a complete reaction mechanism, which we'll talk about later, then you should be able to determine the rate equation. Okay? But usually what happens is we use experimental data to determine the rate equation, and then we try to figure out the reaction mechanism based on the rate equation. Okay? But if you know the entire mechanism, then you also could find the rate equation. All right, so again, we'll talk about that later. So how do we use experimental data to determine reactant order? All right, so here I'm trying to make the numbers pretty simple, okay? And usually on the AP exam, they're pretty simple, especially if it's on a multiple choice question. But this is the kind of data we would be talking about. So you would be given initial concentrations of your reactants and a few different trials. So trial 1, we mixed 0.3 molar hydrogen with 0.3 molar nitrogen, and we measured the initial rate of the reaction, and it was here. And notice the rate of reaction here is molarity per second, okay? And then we did the same thing in trial 2, measured the initial rate. In trial 3, we measured the initial rate, and there might be 4, 5, 6 trials, whatever, okay? So what you're trying to do is you have to compare 2 different trials, and if I want to figure out the order with respect to hydrogen, I want to find 2 trials where I changed the concentration of hydrogen, but I kept nitrogen constant. And if I wanted to figure out the reactant order with respect to nitrogen, I want to find 2 trials where I changed the concentration of nitrogen, but I kept the hydrogen constant, okay? So if we look at trial 2 and trial 1, notice that we kept hydrogen constant, but we did change the nitrogen, okay? And again, it might not be always perfect data and non-calculator friendly, okay? But what we would do is see, okay, well, what change did we make to nitrogen? And so it's quite simple to see that we, from trial 2 to trial 1, we doubled the concentration of nitrogen, right? We went from 0.15 to 0.30. Okay, so we doubled the concentration of nitrogen. What happened to the rate? Well, the rate went from 0.1 to 0.2, so the rate also doubled. So we kept hydrogen constant, we doubled the concentration of nitrogen, the rate also doubled. That means nitrogen is first order. Okay, so from the data, we determined that nitrogen is a first order reactant. Okay, so now let's look at hydrogen. Let's find where we kept nitrogen constant. Okay, so if we look at trial 2 and trial 3, 0.15, 0.15 for nitrogen. So between trial 2 and trial 3, we kept the nitrogen constant. But what did we do to the hydrogen? We doubled it. Okay, so we doubled the concentration of hydrogen and we kept nitrogen constant. What happened to the rate? It went from 0.1 to 0.4. The rate quadrupled. We doubled the reactant, but the rate quadrupled. So that means hydrogen is second order. So from this experimental data, we can determine that hydrogen is second order and nitrogen is first order. So if I want to write the rate equation, okay, so again, let's understand what we did. Looking at the data, we compared trial 2 to trial 1. Why? Because hydrogen was held constant and we doubled nitrogen. And then we noticed that the rate also doubled, so we know nitrogen is first order. So we figured out nitrogen was first order comparing trials 2 and trial 1. Okay? Looking at, to figure out the hydrogen order, we looked at trials 2 and 3. Why there? Because we kept nitrogen constant between those two trials, and we doubled the hydrogen. And we noticed that when doubling the hydrogen, the rate gets quadrupled, so we know that hydrogen is second order. Okay? So now we know our rate law. We could say rate equals K times the concentration of hydrogen squared times the concentration of nitrogen raised to the first power. So we have our rate equation. So that would be, the answer to question 1. What's our rate equation? Okay. Then maybe question 2 is what's the reaction order? Well, the reaction order is just the sum of the reactant orders, so 2 plus 1 in this case, so our reaction order is 3. Okay. So once we figure out the rate law and we know the reaction order, the next thing that usually gets asked is calculate K, calculate the rate constant. Okay. So all you have to do there is, again, you have to go back to your trial data and just pick one trial. It doesn't matter which trial you pick, but let's go ahead and just pick trial 1 and plug in this into the rate equation and solve for K, right? You have the rate, you have the concentrations, so plug them into the rate equation and solve for K. All right, so that's what we would do. We would plug in, so we would say 0.2, the rate, equals K times 0.3 squared times 0.3, and we just solve for K. So K comes out to be 7.4 in this case. But remember, this K is not the same thing as the equilibrium constant. It's the rate constant. They're different things, okay? So what we have to do a lot of times is also include the units for K. So we don't have to do that for the equilibrium constant. We usually never include the units for the rate, for the equilibrium constant. But a lot of times, I guarantee there'll be one question, at least one question on either the multiple choice or the free response on the AP exam where you have to solve for K and include the correct units. Okay, so if we remember this equation, okay, this will always be the correct units of K. The units for K for rate constant is going to be 1 over molarity raised to the reaction order minus 1 times the unit of time, so 1 over time. Okay, so in our scenario, in this scenario, remember our reaction order was 3, right? 2 plus 1, our reaction order was 3. So the units for K, we already solved for the value, 7.4, but the units would be 1 over molarity squared. Why? Because the reaction order was 3, but it's reaction order minus 1. So 3 minus 1 is 2. So 1 over molarity squared. And the unit of time, if we go back to our data table, our rate was measured in molarity per second. So our unit of time is second here. Sometimes I've seen it molarity per minute. I've never really seen it molarity per hour or per year or anything, but it could be. But normally it's seconds or minutes. And the SI unit for time is seconds. So a lot of time it is seconds. But watch out. If this was molarity per minute, then my unit of K here would be 1 over molarity squared times minutes. Okay, so that would be my units. And it would be okay to write them like that. But understand they could be expressed a lot of different ways. So if you want to write it like that because you're memorizing this equation to quickly come up with the units of K, that's fine. But understand 1 over molarity would be molarity to the negative 1. So 1 over molarity squared would be molarity to the negative 2. And 1 over seconds is seconds to the negative 1. So we could write it like this. All right. That's one way. That's another way you could write this. So these units are the same thing as those units, okay? Now, another way to do it is, remember, capital M means moles per liter, and the way you could write moles per liter is moles times liters to the negative 1. But now, if you do 1 over molarity, that's liters over moles. So another way to write this is liters squared times moles to the -2 times seconds to the -1. So this, and this are all the same unit. It's the same thing, just expressed a little bit differently. So, watch out for that. You don't have to write it like this. If you're asked for the units of K, you can just leave it like this. But you might, if it was multiple choice, you might see it written this way. So understand what that means. Okay. All right. So units for K depend on the order of the reaction, right? If the reaction was a fourth order reaction, then this would be 3, 1 over molarity cubed, right? If it was a first order reactant, then it would be 1 over molarity raised to the 0 power. So if you had a first order reaction, the units of K would just be 1 over seconds, or seconds to the -1, or 1 over minutes, minutes to the -1, right? So it depends on the reaction order, and then also depends on the unit of time the rate was measured in. So usually seconds, sometimes minutes, but just look at the data table. If you're given the data table, it tells you what the units of the rate were, and if it's seconds, then that's the unit of time that we need to use in this kind of shortcut to calculate the units of K. All right, so hopefully you kind of get that. We'll talk about how to determine the differential rate law given a reaction mechanism next time, and talk what mechanisms are. But right now, that's really all I wanted to share with you today. So hopefully that helps, and hope you're having a good spring break.